Curvilinear coordinate systems 5 perform the line integral, contour integral dr dot e theta hat, where e theta hat is a spherical basis vector and c is the quarter circle of unit radius lying in one quadrant of the Cartesian xz plane shown below. And we're going to evaluate this integral in Cartesian coordinates in this video. And what happens to the value of the integral if the direction along C is reversed? We can think about that later. Now, our job is to write e theta hat and dr vectors in Cartesian coordinate system. So before we did it in spherical coordinates, that was straightforward. We know that the answer is minus pi over 2. Now, in Cartesian coordinates, the position vector r is given as x ex hat plus y ey hat plus z ez hat. And this can be written in terms of the spherical coordinates. X is r sine theta cosine phi in ex hat direction plus y is r sine theta, this time sine phi in ey hat direction, and then we have r cosine theta in ez hat direction, and we're now on the xz plane, which means our angle phi is 0 degrees. This is 0 degrees. Okay, so our position vector with phi is equal to 0 degrees is going to become, because this is cosine 0 is 1, r sine theta ex hat, r sine theta ex hat plus sine phi is 0, which means this term is 0, but we have r cosine theta ez hat. R cosine theta ez hat. Okay. Now, if I take a derivative of the position vector with respect to theta, then I will obtain here cosine theta, here minus sine theta. So I will have del r del theta is equal to r cosine theta ex hat minus r sine theta ez hat. Now, if I look at the magnitude of this del r del theta, it's going to be r square root of cosine square plus sine square. So this will be r cosine square theta plus sine square theta. This is inside the square root. Therefore, this is just simply equal to r. Now I'm ready to write e theta hat. E theta hat is del r del theta, this derivative of the displacement with respect to theta, divided by the scale factor h theta, which is the magnitude of this. That's r. So we have this divided by r, giving us cosine theta ex hat minus sine theta ez hat. All right. And now we have the transformation between Cartesian and spherical coordinates. X is equal to r sine theta cosine phi But since phi is equal to 0 degrees, this is equal to r sine theta. Phi is 0 degrees on the xz plane. Y is equal to r sine theta sine phi, which is 0 because phi is 0. And c is equal to r cosine theta. So that's what we just did in calculating the scale factors. And r, the radius, is square root of x squared plus y squared plus z squared. And since y is equal to 0 on this path, we have square root of x squared plus z squared. X squared plus z squared square root. And what is that equal to? Square root of x squared plus z squared on this quadrant of a circle is equal to 1. The radius is equal to 1. So this is equal to 1. All right, so this is true on this path. All right, so that also implies that z squared is equal to 1 minus x squared. So we're ready to write e theta hat in terms of Cartesian coordinates. Now e theta hat, our spherical unit vector e theta hat, is cosine theta ex hat, but cosine theta is z over r, but r is equal to 1, so it is z ex hat, z ex hat, and then we have sine theta, but sine theta is x over r, and r is equal to 1, so that's x, but we have minus sine theta here, so this is going to be minus x ez hat. This is our unit vector. And the displacement vector dr is equal to dx ex hat plus dy ey hat plus dz ez hat, but because we're not moving on the y-axis, it is plus dz ez hat. We have y is equal to 0 and dy is equal to 0 as well. All right. So let's do this. Okay, so we have noted that dy is equal to 0. Now we're ready to write the dot product dr dot e theta hat. As you can see, we have ex hat dot ex hat z dx. So we're going to have z dx. And for ez hat dot ez hat, we have minus x dz. So this is minus x dz. The other cross terms are 0. And we also know that z is square root of 1 minus x squared. So we can write 1 minus x squared square root dx. And x is square root 1 minus z squared also. 1 minus z squared square root dz. Okay, now we're ready to perform the integral. The contour integral dr dot e theta hat is the integral of square root 1 minus x squared dx minus the integral of square root 1 minus z squared dz. Now we have to determine the limits of this integration. X goes from 1 to 0, z goes from 0 to 1. So x goes from 1 to 0, z goes from 0 to 1. All right. And I can basically, because z is a dummy variable here, replace it by x. And I can say that this is minus the integral 0 to 1 square root of 1 minus x squared dx, that's the first integral, minus the integral 0 to 1 square root of 1 minus x squared. X or z doesn't matter, it's just a integration variable. So I have replaced z with x. Now you can see that these two integrals are identical, so I have a minus 2 times the integral 0 to 1 square root of 1 minus x squared dx. And let's call this star. Now I'm going to, in order to perform this integral, I'm going to call x is equal to cosine theta, dx is equal to sine theta d theta, and with that square root of 1 minus x squared will become, let's take it here, and square root of 1 minus x squared will be square root of 1 minus cosine square, which is sine theta. Okay, so with this substitution, I'm going to have this integral equal to minus 2 times integral from theta is equal to, so if x is equal to 0, that means theta is equal to pi over 2. If x is equal to 1, that means theta is equal to 0. So this integral is from pi over 2 to 0. And square root of 1 minus x squared is sine theta, dx is sine theta d theta. So I have sine squared theta d theta. And for sine squared theta, I can substitute using the half angle formula for cosine 2 theta. 1 minus cosine 2 theta over 2 d theta. Cosine 2 theta, remember, is 1 minus 2 sine squared theta. So 1 minus 2 sine squared theta, 1's will cancel, minus will become plus, 2's will cancel, so I will obtain sine squared theta. Okay, and now you can see that these 2's will cancel, minus 2 and plus 2, and using the minus sign, we're going to have cosine 2 theta minus 1 d theta. So let's just make sure that x is equal to 0 implies cosine pi over 2, and x equals 1 implies cosine 0. Okay, pi over 2 to 0. And this will give me integral 0 to pi over 2, 1 minus cosine 2 theta d theta, operating the minus sign on the integration limits. So I will obtain the integral of cosine 2 theta is 1 over 2. The integral of d theta is theta. And the integral of cosine 2 theta is minus 1 over 2 sine 2 theta. And this will be evaluated between 0 and pi over 2. Okay, so this is going to give me an answer of pi over 2 minus 0. And this is going to give me sine pi and sine 0, which is 0. So this turns out to be pi over 2. So I have to check the signs here to make sure that I did it correctly. Okay, so for dr dot e theta hat, I had dx z dx minus x dz. All right. So for minus sine theta, I have substituted minus x. And this gave me, since z is equal to square root of 1 minus x squared dx and x is equal to square root of 1 minus z squared dz, x goes from 1 to 0, z goes from 0 to 1, which means this is minus integral from 0 to 1, square root 1 minus x squared dx, and the other one is the same. So this is minus 2 times square root 1 minus x squared dx. Then I made the substitution x is equal to cosine theta, which gave me sine theta. And for the derivative here, this is where I have a mistake. Derivative of cosine is minus sine theta d theta. So because of the minus sign here for dx, I'm going to get a plus sign on this one and a plus sign on this one, which means this is going to be coming with a minus sign. Let's see. So if I change the order of the integration limits, this is going to become minus, and then here I have a minus sign as well. So this will be minus pi over 2 plus 0, and the answer is minus pi over 2. So my mistake was here, dx is equal to minus sine theta d theta. So this is going to give me, for the final answer, the contour integral dr dot e theta hat is equal to minus pi over 2. Remember that this was the answer we obtained using the spherical coordinates initially. So we have to obtain the same answer using the Cartesian coordinates. Okay, now in Cartesian coordinates, I started out by writing the position vector x ex hat, y ey hat, z ez hat. In terms of spherical coordinates, r sine theta, r sine theta cosine phi, r sine theta sine phi, and r cosine theta ez hat. Because we are working on the xc plane, phi is equal to 0, which means this term is 0 and this term is r sine theta. So we have r sine theta ex hat plus r cosine theta ez hat. Then we take a derivative with respect to theta. We obtain r cosine theta ex hat minus r sine theta ez hat. Its magnitude is r, so dividing it by the magnitude, we obtain the unit vector e theta hat cosine theta ex hat minus sine theta ez hat. But we have to write cosine theta and sine theta in terms of Cartesian coordinates. Cosine theta is z over r, but r is equal to 1, so it is cosine, so it's just z ex hat, and minus sine theta is minus x over r, and r is equal to 1, so this is minus x ez hat. Since y is equal to 0, dy is equal to 0, so we have dx for the displacement, we have dx ex hat plus dz ez hat. Dy is equal to 0. Okay, so now the dot product dr dot e theta hat is z dx minus x dz, and x and z are related as square root of x squared plus z squared is equal to 1 because we're on this circular path, unit circle. And we can replace z with square root 1 minus x squared, x with square root 1 minus z squared. Now we can do the integration. Now we see that x goes from 1 to 0, z goes from 0 to 1 in this integral. And we can write this as minus the integral from 0 to 1. So that's what I did here. And replace z with x, so it doesn't matter, this is the integration variable. So I have minus twice the integral 0 to 1 square root 1 minus x squared dx. If I call x cosine theta, dx is minus sine theta d theta, and square root of 1 minus x squared is sine theta. 1 minus cosine square theta, square root is sine theta. So I will obtain minus sine square theta d theta for this one. So minus sine square theta d theta, but there's a minus sign here, becomes plus 2 integral from pi over 2 to 0. Why? Because x equals 0 implies cosine pi over 2, x equals 1 implies cosine 0, pi over 2 to 0, sine square theta d theta. Sine square theta can be replaced with 1 minus cosine 2 theta over 2. 2's will cancel. If I change the integration limits, if I switch them, I have to introduce a minus sign. 0 to pi over 2, 1 minus cosine 2 theta d theta. This gives me theta. This one gives me minus 1 over 2 sine 2 theta. Operating the minus sign, this becomes plus, this becomes minus. So 0 to pi over 2 minus theta is minus pi over 2. The other one is sine pi and sine 0 at these two integration limits, which are 0. So this gives me no contribution. So my final answer is minus pi over 2, as I was expecting from the calculation using spherical coordinates.